All right. Sorry, let's start. Yeah, we're good. Perfect. So hello everyone. Again, I'm Lorena, PhD researcher at the Department of Geoinformatics at the University of Salzburg. I'm going to present you tools and packages to current process Sentinel-1 and Sentinel-2 data with R and Python. This is part 2, and this is my contribution to the OpenGeoHub 2023 Poznan. So, as I said, this is part 2. So this is just a recap of the plan for the sessions. We're in part 2. And today we're gonna mainly focus on Sentinel-2 data with R and Python. So skip to that. And from yesterday, we saw Sentinel-1. Today we will check Sentinel-2 and we will work with R and Python. Wish me luck. I'm gonna try to run 2 Docker containers at the same time with the Zoom call. So let's hope that everything goes well. Cool. And thank you for the people who are here. You're so hardcore after the nice evening we had. So it's really cool to see you all. Good. Let's just start with some quick Sentinel-2 quick facts. Yesterday there was already a question on what's the difference between Sentinel-2 and Landsat. So I started ranting already about all this, but just telling a bit about it. But just as a recap, Sentinel-2 is a high spatial resolution optical imagery. So you have 10 meters, 20 meters, 60 meters. It's systematically acquired over land and coastal waters. We have 2 satellites in orbit right now, Sentinel-2A and Sentinel-2B. There will be a third one, Sentinel-C, in 2024, which just give us way more data. So we can also get data here more or less around every 6 days, which is great. And it was launched in 2015, Sentinel-1A and Sentinel-2A and Sentinel-2B was like in 2016, more or less. It's multispectral data, so completely different from what we were looking at yesterday, but probably something that you're more familiar with remote sensing. Usually start with this. It's 13 bands. It's in the visible, near infrared, shortwave infrared, and it has no thermal bands, but there are some people trying to also emulate some thermal stuff, but that's a bit more advanced. Yeah. So that's basically it from the quick intro. So now we're gonna let's get to it. Just get to it. Yeah. So today is gonna be a bit back and forth. I don't know if you managed to run both Docker containers at the same time. What I do is basically have, like, I open 2 PowerShells in my case because I'm using Windows. And in one, I run one container, and then on the other one, I run the other container. It's just so that they both keep running, because it's not like you can then type anything here. And then you'll have these 2, like the Jupyter Lab, as I showed yesterday. You just copy the link on top, and then you'll get here. And then to open the RStudio server, you just type localhost.8786, and you should have your RStudio open. If you're not working with this Docker container, you're just working with RStudio, then probably you'll have less problems than me. So that's good. Good. Yesterday I didn't go through it, but the way you find these notebooks, I think people are smart enough that they found out, but this is the main directory that is mounted on the Docker, right? So that's why you have to put this, you have to navigate to the place where you downloaded all the stuff. And then that is inside this Docker container. So you get all this information. So you have this data, Docker files, which is where you can do the stuff, some figures, and then you have the notebooks. So in the notebooks, you have 2 directories, Jupyter and Quarto. This is Jupyter, and this is the Sentinel-2 notebook. And then for RStudio, you have the same setting. So you have notebooks, you go to Quarto, and then this is the Sentinel-2 Quarto document, which is also more or less notebook. So I hope I don't confuse you, and if it gets confusing, let me know. But I will start with Python and then show you how to do the same in R, okay? So like we're gonna do a bit of a comparison, okay? I can do this with Python, how does it work in R, and back and forth, okay? Good, let's see if that works. Okay. This should be good. I hope this is good and visible. All right. So I'm jumping right into accessing data. So probably if you've ever worked with Sentinel-2 or any other type of optical data, have you? Can I get a raise of hands if you work with optical data? Yeah, sure. Amazing. I don't know if when you first started, you had to like download all the data because that was like a common thing, right? I remember like looking for so much data in the OCGS Landsat thing and then getting so much information into my laptop. Hello. That's quite intense, let's say. But nowadays, in modern times, we can fetch the data in a whole new way, right? So I'm gonna talk to you today about the Stack API. First, I just included all the libraries that we need. There's always like a hint of what each library does, but let me know if something's not clear, and it will become clear also when we go further. But I'm gonna start with this Stack thing. So Stack stands for Spatial Temporal Asset Catalog. It's a common language to describe geospatial information. So you can work more easily with it. It's indexed and it's easily discoverable. Okay, so that's basically, imagine this. You have these repositories of data like Sentinel or like SentinelHub or like Copernicus data services or whatever. What they did is just like have this common standard of metadata that just helps you find it easier, right? So then you have just like this huge dictionary of, okay, this is the data you have here, and this is the URL where you can find it, right? But it's all in one single thing so that you can basically search. It's a search catalog, okay? So yeah, it's, I don't know an analogy, but it's a search catalog. So it looks like this, and you will have here like all the different repositories where you can get the data. So you have Clodias, if you're familiar with it. Digital Earth Africa also has something. If people remember Edserstock, OpenGeoHub also has stuff. Yeah, for example, they have this connection of the Google Earth Engine OpenGeoHub thing. So like with OpenGeoHub, you can get Google Earth Engine data. So that's one. You have the Microsoft Planetary Computer that I was talking about yesterday. Yeah, you name it, you have a lot. Here's the OpenGeoHub platform. Some of them are public and some of them are protected, and you'll see it here. Some of them are a catalog, some of them are an API. An API usually is that you can just query, like that you can query and also get the data. A catalog is that you can more or less can just like check what is there, but then getting the data is a little bit different. So you will need to like have more credentials to access and so on, or another way to access it. But it is there on Stack so that you know which data is available everywhere. Okay. So today we're going to work with the Earth. Where is it? Earth Search, which is a Stack API of public data sets on Amazon Web Services, meaning that you don't need to get any credentials to get this. So like for Sentinel-2 in this case, you can just access the data without the need to have an account, for example, on SentinelHub, that you usually need to have some credits or something like this to fetch the data. So that's not super nice. It's just nicer if you can do it without, right? And this is the collections that you get in this catalog. So let's look at that over here. So as I said, we're gonna do Earth Search catalog. And for this whole thing in Python, we're going to work with this PyStack client, which is basically a client to access the Stack catalog with Python. Very self-explanatory. So we first have to get this Stack API URL. And where did I get that from? It's from here. So on the Stack catalog, you have it really like on the second part, you have the URL that you're going to query. So I copy that here. And we start fetching data. So we're gonna create this, what they call a client, and we tell the client to open the URL for us. So like client equals PyStack, and then you have the API URL, and you already have this client that is gonna give you the connection to all the data that is right there, right? So let's anyway run this, and then the next line, what it's asking is to print all the collections. So here you will see the collections that are available on this specific let's call it bucket. So you have this Copernicus DM, NIPE, Sentinel-2, level 2A, level 1C, Landsat. Then we have the Copernicus DM at 90 meters resolution, and Sentinel-1 GRD. As I was saying yesterday, you sometimes have this as well. I think for the Sentinel-1, you do have to have credentials, but for all the others, it should be fine. And as you will see, this is exactly what you have here. So I'm just basically asking Stack, what is there? So it's in collections. So then I get collection, and then I get all the collections that are in this particular Stack repo. Yeah, so now we're going to focus on Sentinel-2 level 2A. And if you don't know what level 2A is, we're going to take a look. So these are the different levels. It is not visible. Yeah, that's more visible, right? So you have level 0, again, not something that you want to directly work with. Level 0 consolidated. This is just stuff that the people really working on ESA are working with and doing all this pre-processing for us. In level 1A, some radiometric corrections happen. Level 1B, there's some sampling, conversion to reflectances, so you don't have digital numbers, but reflectances. And on level 1C, you have already an atmospheric correction. So you get TOA reflectance at this point. Yeah, so TOA is top of the atmosphere reflectance. And that's one of the most common ways of working with Sentinel-2 until a few years, because we didn't have the next one, but now more and more catalogs allow you to also fetch level 2A, which is surface reflectance. So it's basically from the TOA data, you're gonna do an extra processing step where you're gonna get directly surface reflectance values. That means without any atmospheric influence. Probably if you have been working with optical data for some time, you must have done this step locally. If you do it with QGIS, there is this plugin that lets you do this. So that's basically what they now do for us, so we don't have to do an extra thing. So more towards this analysis ready data era that we're living in. Yeah. So that's level 2A. And you can look at all the other levels if you want to take a look at that. So then we'll say, okay, this is the collection that I'm going to get, this Sentinel-2 level 2A. And from yesterday, remember we had like this definition of where we want to get our data from. We do exactly the same here. We're going to give this spatial and temporal extent. So we have the coordinates and we have a date range. This is the way to define the date range. So like in one single string, you have the start date, the end date, and you join it with a backslash. And the longitude and latitude, now it's a point in Poznan, because we're in Poznan. And we call it into this point object that is a Shapley point. So Shapley is in charge of all the very low level geometries in Python. So SF does way, like in R, SF has way more capacities to like work directly with the points, and then you can work it as a data frame and everything. Shapley is here more just in charge of the geometry part. So we have this point, and we can pass then all these arguments to our search. So very similar to yesterday's, we have our client, we have the command search, and then we're going to say, okay, I want you to find this collection. So the collection we defined up here. We can also ask for more collections. That's why you can pass it as a list. So if you would like to fetch not only Sentinel-2, but also Landsat, you can do that, right? You can do it in one single query. We're going to tell it that it has to intersect with this point. So this point has to be the Shapley point. And we have the date time already defined. So we're going to get our search. And then we can see how many items are on my collection. So I found 61 items. What you can also do is some extra queries based on the data that you have available on the items. So for example, again, it's not nice to look at the items just like that. So I created a pandas data frame so that we can read it easier. Yesterday I did a pandas, or maybe it was a geopandas, but you have the geometry right here. So like the polygon of what is covered. And we have the platform, constellation, what instrument it is. So this is multispectral instrument. And then you have some useful stuff. Like, for example, you have the cloud cover. And that's something that you can use to query, right? Something that has less than 10% clouds or something like this. You have the projection that this data is on, the UTM zone, blah, blah, couple of things. And the granule ID, yeah, you name it, you have a lot of information from this one. And so what we can do, if we go back to our search, is use the query part to say, okay, from this EO cloud cover, I want it to be lower than 10. And it has to be the same name as here. And this is here. So that's why it's EO to like colon cloud cover, cloud underscore cover. And then as you see, these are in percentage. So we can directly just say, I want this to be below 10. And then we will get something, a little bit more filtered collection of our data. So remember before we had 61, now we have 8 items that correspond to our query. Okay. So that's, yeah, that's way less. So we can take a look at them again. You have quite some, and here you see which satellite it is, to A or to B, and so on. So yeah, we can get this, and what we can do, for example, is just take a look at the cloud cover over time. So this is how it looks like. So because we query this with less, can do it without the query, so that we can see a bit more of the cloud cover itself. Do I need to do this? Yeah. What I'm doing here is just plotting the date against the cloud cover. And you will see that indeed over our area in Poznan. So over our area in Poznan, we had quite some days with cloud cover. That's usual. If you've been working with this, you know that this is always the case. But we have some elements that are rescuable. Be a little bit cautious with this EO cloud cover from Sentinel-2 that is really in the metadata for some time. It's been noticed that it's not really accurate, especially in like in the tropics. Sometimes it's like stated that it's a lot of cloud cover, but actually there's not so much cloud cover. So there's something on the atmosphere that is being detected by the algorithm as cloud cover. And for this reason, there's like a lot of information that has been lost, like people who just query things. Like I'm from Ecuador, I've always been querying stuff. And I was just losing a bunch of scenes that I didn't know were useful because this was a little bit flawed. They're definitely working on this, and I think they already have it corrected. But if you have older scenes, this might be a problem. There's an interesting paper that I will put on the Mattermost for people to take a look, and I'll also put it here, that looks at this bias of what happened with all this loss of information and how much more we could have done with it. I think with Lancet as well or something. I'll definitely put the paper on. So be a little bit careful with this, but now we're going to trust on the data that they give us, and we're going to query it like this. So let's go back to our query. We're going to have cloud cover for 10. And then if we do our plot again, I already showed this. We have not so comprehensive time series, but at least we don't have so many clouds. Of course, you can like work with this and make it less and less. Yeah. So now we can like look at the properties of one single item. And I'm gonna select one that has a low cloud cover. So for that, what I did was just, again, some filtering on the data frame. So I'm asking for some cloud cover that's only under 2. And there's also another property of these items that's called no data pixel percentage. So like if you have no data, because sometimes you have like this scene that's going and you have like this whole strip that has a bunch of no data. So that's not so useful, but you maybe don't want to get all this information in. So you can also filter by that. And we get like 3 that correspond to our query. So you'll see here, the EO cloud cover is very low. And then this no data should be somewhere here. Otherwise, I cannot process it. But okay, let's trust that it's doing it good. Good. So we can take a look at the first one that comes from our result. So this is the item. This geometry is basically what is covered by, like, the scene is covering this square, let's say. This is, we can fetch all these properties, right, just with this point thing. So like you have datetime, so which exact date this scene corresponds to, and we can get all the other properties. So we have when it was created, which constellation, platform, cloud cover, tiles. You also have now with level 2A some more processing on how much water there is, what is the vegetation percentage, what is the cloud shadow percentage. So if you're really looking into these kind of things, it's also can be something good to query, because then you'll get a little bit filter information. But again, always try to that what you're getting is really what you want, because you can say, yeah, okay, I want this very low cloud, but your study area is very small in comparison to the whole scene. And it could be that where the cloud, like there was no clouds over that very small area, but was cloudy, right? So then you're losing that because, yeah, it was there, right? So there are also ways to get a pixel kind of representation of the clouds, and I will show you later. And that's also what you can do with Earth Engine, right? You can ask it by pixel, so not by the whole scene, but by pixel, where do I don't have any clouds. That's also what my colleagues do with the Cent2Cube implementation, where they have this semantic layer when you can really say by pixel, okay, here the probability of cloud is high, so then I don't use this pixel, but here it's low, so the querying gets a little bit more localized to your real study area. So that's also something you can do, and I will show it in the R part of this. Okay, and we can also take a look at the bands that are available. So that we can do with accessing the assets and the keys of the assets. So if you don't put keys, I think you get like this whole thing. So like each of the bands. So I'm just asking from this dictionary to give me the names of the values, because otherwise I just get all this stuff. So these are all the bands that are available, right? So you have this blue, coastal, green, but you also have like things like a thumbnail, you have a visual representation. In this case, we have this JP2 format of getting the data. So as you see, this is just basically repeated, but this is in JP2 format. So it's not TIFF, but JP2, that's it. But you can fetch all of this. So we can take a look, for example, at the thumbnail, so to see what we are dealing with. So for that, we go to assets, we ask for the thumbnail, which is here, and then we get the URL that was shown before. So that's how we're gonna get it. And then I'm using this Python image just to show the URL. So this is the thumbnail. This is the scene with very low cloud cover, with not so many no data values. That's what I'm looking at. So you can have a quick overview. As you see, this is running live. So this was fast. And then you see that you can easily fetch this and take a look at what scene you're working with without the need to downloading or anything. That's working great. We can also take a look at the single bands. This might take a little bit longer, I think, but you can also do that. So let me get this running because this one takes a while. So for that, you again can call the red band, and you can see also what extra fields we have. So we have, for example, here for this particular band of this particular image, you have all the descriptions, but you also have the projection, we have spatial resolution, and a bunch of other things. So again, as yesterday, if you remember, we can directly call this data in with RioXarray without the need to download anything. We can just use this URL, and then we can just open this, right? So for that, we use RioXarray and then open raster.io. We give it the URL, and this decode coordinates this so that nothing goes crazy. I think I had an error when I didn't have it. That's why I added it, but cannot completely remember why, but use it. So that's why it's there. And now we can also plot the data. And again, I'm using this iCell, so I'm slicing it so that I don't get like this whole scene now, because when I plot, I'm really fetching the data. As yesterday, then I'm really asking, okay, please bring the data in because I want to see how it looks like. So this is gonna take a little bit longer, and that's why we have this selection. So here you'll see this is the, wait, for some reason the F11 works for getting out, but not in. So this is the red band. Okay, not in super red colors. This is VDD, one of the famous palettes, but still. This is the red band of my collection of small things. So you'll see this is Poznan. Probably people who are from Poznan will have an idea of where exactly this is. And you have then here this surface reflectance numbers of your area for the band red. So we can also do an RGB representation. And remember, we had this visual thing at the top. So that's also something that we can take a look at. Again, if you see here, we have this visual. That means that it's just like combining the red, green, and blue together so that we can just directly get an RGB. So we don't need to call each of the bands, and we can just directly fetch it. And again, I do a selection, and here you have it. This is how the RGB representation of that specific part looks like. Okay, so this is an interesting way of where like you can just easily check the data you have, no any selections or anything. Yeah, just working with the Stack API. So at this point, I am gonna show you how to do all this with the R implementation as well. Okay. So I hope you remember every single detail that I talked about, because I'm going to ask a lot of questions of what the difference are. Just this. But I might ask a couple of questions. Okay, so we go to our RStudio. What I like to do to make it easier for me is have the console here and the environment over here, because then I can. It's easier for me to work, but don't get confused. And to make it even less confusing, I'm just gonna open this completely outside. So then this looks like a Jupyter notebook. Okay, so should work. Okay, so don't get confused. This doesn't look like R. It does. I'm just like opening just a Quarto document outside. Okay, good. So again, we have all the libraries in R. You'll see some different libraries here. Again, all these explanations of what each of them does. You will see some of them have their counterparts on Python. So we'll get to that while we go through. So in this part, we're gonna go and define an extent one more time. To define an extent, again, we need to have an AOI and we need to have time period. So for the people who also wanted to go to the OpenStreetMap session, but thought maybe we go here, I'm going to show one function that probably was on the OpenStreetMap session. So that's, we're going to fetch data with OSM data, which is a package to just fetch information out of OSM data. And last time I tested was, or no, that was like a week ago. It was not working, but I think it's working now. And so what you have here is a very nice one that I like, where you can get the bounding box of a city or an area in the world, like, or yeah. Mainly I use it for cities because that's way easier. So you had like this get BB is from OSM data, and then you tell it like, I want it from Poznan, Poland. I think I had to add Poland because it was another Poland or something. There was some, like with the geocoding, there was some like overlaps and it was a little bit weird. You can tell it to give it the out format in SF. So SF is, oh wait, I forgot to ask. How many people who are more in Python, into Python are here? Can you raise? Okay, and more people into R? Yeah, that's really a majority. Okay, so you, I know you'll follow along, but okay, SF is the counterpart of GeoPandas, let's say. But yeah, SF was there first, I guess, or at least I would like to think so. So, okay, you have this, you can get this out as an SF polygon. And here I added limit equal 1 because for some reason I was getting a duplicated geometry. But this is just something that you can tell, just give me the first result that you fetch out of this. But of course, it can be that it's not always correct, so we can make sure that the AOI is correct. And for that, I will use TMAP. TMAP is a really great package for visualization of in R for anything that is raster or vector. You can use it for static maps or for interactive maps. So to make it interactive, you can say tmap_mode view, and then you'll get an interactive map right in. And then you have this quick tmap function where you can just pass your data, you get a fill, and I put an alpha, and you should be able to get a really nice plot of your area. So this is Poznan, and this is the bounding box that was fetched from the OSM data file. Okay, so that was the quick OpenStreetMap interlude of you didn't miss everything. Maybe this is something that you might want to also look at OSM data as an option to fetch some OpenStreetMap data. Okay, so we have now our AOI, and we have our time extent. So here I added it as a vector of 2 dates, so the start date and the end date. And we have that in our time extent object. And what I need to pass the data to the search query is a bounding box. So I have here my AOI, and I'm going to compute the bounding box with SF. I call it BB4326 because this is going to be in 4326 or WGS84, because that's how OSM gives me information. So we can compute that, and then we can also get transformation very fast of the same bounding box, but then in 3857. So like Mercator projection, so that we can later pass it to plotting or other type of information that we need to get a different projection in. So there's a reason why this is computed. I will show you later. Okay, so we have our bounding boxes, and now we can start, like we have defined extent. So now we can start querying the data. So the counterpart of PyStack client in R is RStack. So RStack, I think it's, yeah, developed by the Brazilian Data Cube. So it's a really, really nice package. I mean, the Brazilian Data Cube are doing a lot of things to also get this data and everything, and they did this counterpart to get stack information. So that's quite a nice contribution for that. And it's now we're going to start looking at how we get started with the API. So again, as before, we're going to work with Earth search, and we just again give the URL, and we can get the collection. So this looks very similar to what we had with Python, right? Like you say, okay, I want this from this client, I want the collection. It's a little bit less. Let's look at it. A little bit less lines of code, probably, because that's usually the case when you're working with R. So here we had to like define the API URL, and then first the client, and then the collection. Well, it's a bit similar. So yeah, we have the stack function that will just fetch everything, like what is called the client in Python. And then we can get the collections out of that with this get request. Okay. So every time you want to really fetch something, you do this get request, and you will get the response from the Stack API. So here we have our collection, Sentinel, Sentinel-2, level 2A, level 1C, Sentinel-2A COGS, that means cloud optimized geotiffs. So that's just a faster rendering. It's a great type of extension now. We're using, it's used a lot for this saving data on the cloud. We have Landsat 8, and yeah. Does someone notice any difference between this collection and the collection I showed before on Python? I told you there will be tricky questions. Yeah, Sentinel-1 is missing, right? The reason for this is that in this case, I'm using the version 0 of this stack collection of Earth data and not version 1, because for some reason, this was not working so properly with R. I guess it will eventually, but this is the reason why the collections look different. So it's also, we didn't have this Sentinel-2 cogs before, because now on the version 1, everything is cloud optimized geotiffs. So you don't have any other option. And of course, they included Sentinel-1. So that's the reason why things are different, but it still works and you still get the data. So you already passed the quiz. But yeah, that's the reason why this looks like this. So okay, now we can do a search. Exactly as we did with Python, we can start a search. So first we have to give it the S object, which is the stack client in this case. So we have S, and we're gonna do a stack search. We give it the collection. So I'm gonna ask for the cloud optimized geotiff Sentinel-2 level 2A, and I'm gonna give it the bounding box. Here I'm gonna give the bounding box in WGS84. The reason why I pass it like this is because it really needs an exact order of the X minimum, the Y minimum, X max, Y max. That's why I pass it like this. Here I have to give datetime. Remember in Python, I show you that you needed to collate everything with a backslash. Here I'm doing the same. So I just put it with code. And I ask for a limit of 500 so that I don't get a lot of data, but I don't think we will reach that much with our stuff. So this should be okay. So we got 144 features matching here. And then, well, the printing method is a little bit different. So you get like the first ones, one of the first images that you get, and you get the assets. Remember the assets that we could see before when we did asset keys, which is basically the bands that we have for this particular collection of information. Yeah. So we can explore this again as an SF object. So before I converted it into a GeoPandas, so now we can convert it into an SF, which prints a little bit wonky on this quarto, but you can still get an idea. You have the geometry, you have projections, platform. So this is a little bit harder to read, but we can just take a look at the initial, like the names with this glimpse, just lets you see a bit how the data looks like. So you have the product ID, you have the projection, you have the what instrument it is. It's always going to be MSI, and you again have this EO cloud cover, for example, where you can again do the querying based on EO cloud cover. This is also something that you can do. So we can now take a look at this EO cloud cover again, as we did before, and we're going to get more or less the same pattern as we got with Python. So that's how I can do it. Here I'm using ggplot. On the X, I have the datetime. I have Y on the cloud cover. I plot points. I plot lines. I group them in one single one because then it knows it's the same thing. And I just use a scale of the date every 2 months so that I don't get a lot of dates down here. That's something that I don't know how to do with Python. And that's why I think this was looking really wonky when we had all the dates, because I don't know how to specify. I'm not so fluent in Python plotting as I am in R plotting. But okay, probably you can do it. I just don't know how. Good. So we can again look at the properties. So, oops. Here. So this is a little bit more readable for one single item. So I'm just getting like items, the features, and feature number 1. Remember in R, you don't index from 0, but you index from 1. So if you ask for feature 0, it would be like, what are you doing? This is not Python. Okay, so it's number 1. And we get the properties. So we have the datetime, the platform, constellation, everything that I was showing before, but you also have the valid cloud cover thing, property. The data coverage is the thing that I was mentioning before when you have an ACE or you don't have an ACE. So we can take a look at that. The valid cloud cover property is also like trying to enhance this cloud cover from this EO thing to get you something more accurate, because as I say, there was some problems with this. So that's what this one is for. So we can filter this as object to get something more precise of what we want. as we did before. So we get this filtering. I just give it a row number because in this case, I don't have an ID per row. I do the filter based on the valid cloud cover. That means if the cloud cover that is given by the EO cloud cover parameter is valid or not. So like it can be either 1 true or 0 false. So like if I have like this EO cloud cover is 0, but actually it's not true, there was a mistake in the algorithm, then this valid cloud cover will be false. This is not valid, so just ignore it. So that's why I'm using this valid cloud cover to get everything that is really correct, let's say. I want everything that has data coverage over 80%, and I want to get just one item. I want to get the one with the minimum cloud cover. So if there are 2 items that have 0, and that's why I needed to get it like this. So like if I don't do this, wait, let's not do that. Okay. I think there are 2 items that have more than, or like that have 0 cloud cover, and that's why I just asked for the first ID and not get everything. So now I save this on item, and then again, I can take a look at the URL with this thumbnail, and I can take a look at how this scene looks like. So far, so good. That's basically what you can do with Python and what you can do with R in terms of searching and querying this stack index catalog for your, for whatever you need to do. So are there any questions so far? Am I going okay or too fast? It's okay, cool. So yeah, you can just choose your weapon and see whatever suits you better. If you want to work with Python or if you want to work with R, at least until this point, you can do it in both. So yeah, that's cool. Because normally I found that a lot of APIs used to work more with Python, but more and more you get R counterparts that let you do this as well. Okay, so now we're gonna go back to Python. I hope this is okay also, the switching, that you're not getting like, what is she doing? So that's why I also like kept it in 2 different, like Jupyter and then RStudio, so that it's clear that I'm switching, because I was thinking of doing everything in one single notebook, but then I thought it would be even more confusing. But I don't know, you will tell me later with your feedback what was better, okay? Good. Yeah. So also, if you want to take a look at fetching only the red band and doing a small plot or something like this, feel free to experiment on R. How would you do the things extra things that I show in Python? How would you do them in R? There will be a way to do it for sure. Okay. So now we're gonna go into how to get not only one scene, because that's really nice to see it, but we don't really want to work only with one because we're in the era of big data. So we want to work with a lot of data. And usually the way to do that nowadays is with data cubes. I think if you've been to the Xcube talk, OpenGeo talk, and probably any other talk in this OpenGeoHub, you will notice that that's really now the trend. So we can also create data cubes with this Stack API. Okay, in this case, we can do what it's called like a data cube on the fly, or not on the fly, on demand. So you can basically find any place in the world that you want to work in, and then you can create this data cube where you can fetch any type of information. So you don't only need to do it with Sentinel-2, you can also get Landsat data on the same data cube, you can get Sentinel-1, and then, or a DEM on top of it. And then with that, you can do whatever crazy thing you want to do. At some points, you will need to define at which resolution you want to do. We're going to go through that. So that means that everything's going to get resampled. So you have to be a little bit careful with how you do this and think about your variables. If this makes sense to resample it at this scale with this type of resampling method and everything. But okay. We're gonna now look how to do a data cube with Python. For that, we're gonna use the package stack. They are very creative with their naming. So we're gonna use stack, which basically means we're gonna stack items, okay? We're gonna limit our data cube only to an area in a post number bounding box. So this is how it's, well, I'm now having commands in R. So there's a file in data called PostNumGeoJSON, and this is the how this looks like, the bounds of it. Yeah, that's it. You have the bounding box of this PostNumGeoJSON file. I mean, I think we can just see. Probably I showed it yesterday. How this looks like. So it looks like this. This is the PostNumGeoJSON file that we're looking at yesterday. We're gonna work with this one again. Yeah. So for this now, we're gonna rely on our previous search. Okay. So let's go back a bit into what this items is, so that we don't get completely crazy, because I'm also not remembering completely. Here. So initially with PyStack, we did the search, right? We told it which collection it has to intersect this point. This is the datetime, and this is the EO cloud cover that I want to have. Then with this items object is basically the search. I want to get the item collection. So all the data that matches my search. So I have this item collection, and this is my object items, okay? So remember here we had 8. So what we're gonna basically do is now create a data cube with these 8 items stacked on top of each other, okay? And that's why we're gonna use items as the base of the function stack. This is gonna be fun, like a tongue twister. Okay, so we have stack dot stack. So here you can start building your cube like this. So we have the items, and here we can give a resolution. So as I said before, Sentinel-2 is what resolution? You can say it. Yes, 10 meters, between 10 and 60 meters, right? So it depends which bands you're gonna use. Normally the visible bands are 10 meters. Then yeah, the more away from the spectrum, you'll get a little bit bigger. But here you can specify a different resolution of how you want to fetch the data. Why we do this, or why I chose 200, just because I want things to go a little bit faster, okay? So like if you ask for it at 10 meters, it's gonna take a while, a very long while. So we don't want that. And actually, let me just, while I'm talking, start, running some things, because I think this one is the most expensive computation that we have today. Okay. Yeah. So we can select this resolution 200 meters so that things are not going crazy, right? Then we give the bounds, and we can give it in latitude, longitude. So that's what's here, footprint, and then this total bounds. That's how you get the latitude, longitude. It's an array, so this will be understood by stack dot stack. You can also give it bounds in any other CRS. And I think then you have to give the CRS, or maybe, yeah, you have to give the CRS. So like if you only give bounds, then you have to give the CRS of which is, yeah, in which projection you're giving the bounds. So it's easier to keep it in that long because it will just understand it. And you have to give the resampling way. So like how you want to resample this. And in this case, we're using a bilinear interpolation. So you can also use nearest neighbor. This is because normally you have 10 meters, 10 meters, 10 meters, but now I'm asking it to do 200. So that means we're gonna have a bunch of pixels in one single pixel, right? So how should this be combined together? What values should it take and everything? So that's why you have to give a resampling technique. So bilinear is just gonna do some equation that gets you everything together, but you can also do nearest neighbor where it starts taking like the value, the average value of the nearest neighbor or something like this. So yeah, that's what the resampling technique basically does. So here, all good. We have our cube. So now it's already printed. And this cube is an X-array data array. They love to do this, that I have to say the word twice all the time. So this is an X-array data array. And as you see here, and I think I showed this yesterday as well, you have all this chunk of data. This is like our data cube. And I like the printing method of X-array because you can really see it's a data cube, right? So you have, this is your like X and Y. So what area is covered in X and Y. And then you have here all the rest of your data, right? So like you have, in this case, apparently 32. So we can take a look at what exactly this is. Wait, here, yeah. So we have 4 dimensions for this data cube, okay? We don't only have time and X and Y, but we also have the band. So in this case, the representation here is choosing to show us the bands. So it has 30, each of the things has 32 bands. And here you will see the extra dimension means that you have 8 timestamps in this data cube, okay? So because it's hard to show 4-dimensional things, that's the way they decide to do it. So I've not used 5, so I don't know how the representation of that is gonna be, but I guess they'll figure it out and you can use a lot of representation. So you have time, which is, yeah, our time for each of the scenes. Then we have the band, which is all the bands that we saw before. So you have all this naming, but then also the JP2. That's why it's such a big data set. And you have X and Y, right? Then you have the CRS. Of this one is 32633 because that's the CRS where the data came from, this UTM representation. And as you see here, we have the resolution of our data cube is 200 meters. Yeah, so that's what we're working with. And again, as I was mentioning yesterday, this is doing some chunking in the back. So that means that even though our data array is 39 megas, and the way it's working now and fetching the data is like parallelizing the back. So it's not gonna get me data until I really ask for it. So you can do a lot of operations already on this array of 39 megas, but in the end, it will only start like the real computation when you really want to fetch the data. So when you want to plot or when you want to extract point information or something like this, then it's when it's really gonna be like, okay, now I really have to execute this whole code. So if you were on the OpenGeo, it's a bit like when Etzer showed how he can have all his code and only log in on the last step, because then is when he needs to do the actual computations. A little bit like this. Yeah. So what we can do with this cube is select only the RGB bands, for example, because as you saw here, we have just a little bit too much redundant data, right? We have all these bands, but then again in this JP2 format, and then you have the thumbnail and the visual and blah, 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 and like, we don't need all this, right? We're not gonna work with all this. You could just take all the bands, or in this case, I'm only gonna get RGB. And with that, for that, you can do a selection. So you can use cube, which is our cube object. I'm gonna select red, green, and blue. And this is the order we need of how it's gonna be selected, right? So we can do that. That's easy. And we can also create multi-composites. In this case, it's gonna be a bit weird because we only have 8 scenes, but you can still do it. So what we can do is what is now called, again, a resampling. So now I've basically here made a cube or created a cube. Let's look at it. Hope this doesn't break. Oops, not EGP, RGB. Yeah. I created first a cube. So this RGB cube is, as you see, just the selection of 3 bands. So instead of having these 32 bands, I only have 3 now. Yeah, so that's much more manageable. And you see that the size of my data cube also was reduced like 10 times. So like this is 39 megas, and now I have only 3 megas right here. So that's just helping with the amount of data that we have. So now we have this RGB, and we can do this also temporal grouping of our data. So in this case, what I'm doing is saying, okay, now my new cube RGB, I'm gonna resample it, or like reduce it based on time. And to say that I want months, then I do MS. These are all the time range formats that you can get to do this. So you can say, I want it yearly, I want it quarterly, I want it hour frequency. And then you have like crazy combinations of things like I want it yearly, but I want it to start in January. I want it yearly, but I want it to start in August, or I want it quarterly from May. So like this X-array time reference is, you can customize it to whatever you want. I discovered it's quite interesting. But okay, in this case, we're gonna use it per month. Yeah, and we're gonna compute the median. So like anything that has to be combined, because it's like all the scenes that are for June and all the scenes that are in July, they're gonna get combined, but we have to tell them how we have to combine the values, right? So in this case, we're gonna compute the median of the values along each of the bands. So the median of the red band, the median of the green band, the median of the blue band, and that's going to be combined over this time dimension, right? And we're going to keep the attributes, meaning that I want to keep all this metadata with me, because otherwise, yeah, I'm losing some information. So this is what we're doing with this monthly, and that's what is printed here. So as you will see here, now we have 3 bands. So that's the same because we're still with RGB. But now we only have 3 points in time because, as I already said, we only have 3 months to group in, okay? Again, you will see the array is getting smaller and smaller. So you have 3 megas, now it's only 1 mega. And yeah, we're trying to make it smaller and smaller. So you will see on the indexes now you have the bands, again, RGB, and you have your time that starts on the first of the month. Okay, that's why it's MS and not only M. So MS means M, but to the start of the month. So that's why it's like this: 1st of June, 1st of July, 1st of August. Okay, so that's what we have now. And what we can do is then ask this data in memory. And that's why I ran this earlier, because that's what takes time. And I think it's worked. So we use this, I have now this cube that is, I'm like looking at it and thinking, okay, it has a nice size, it's only 1 mega, it only has 3, and then the other dimensions, right? So it should be okay and doable. So then I can ask this compute function to really fetch me the data so that I can really work with it. And that's this task function that reads the object in memory, because before that we're not doing that, right? So I do this because I want to plot. I can also directly try to plot without doing compute, but it would just take much, much longer because it has to like get everything in at the same time as plotting. Well, if I do the compute before, it will just have it in memory. So if I need to change one parameter of my plot, I don't want it to start fetching the data every time. So that's why I compute this so that it just works, right? So what I'm doing here now is doing an RGB representation. So that's this plot im show, I guess it's image show. I can tell it which column I want it to use and how I want it to wrap the columns. I want 3 because I have 3 months. The RGB representation is stored in the dimension band. Robust is to do a stretch of my values so that I don't have like these weird artifacts. I don't know what size is. Must be something. And at labels false, also probably for something else. So here you see that I have my 3 months. So this is basically a monthly composite of the data that I have. So that's for June, that's for July, and this is for August. You see that the resolution is not super, like, yeah, but that's because I asked my cube to be 200 meters. So that makes sense, right? Like that's exactly what I can see. But yeah, this is the way that you can get all this information. And as you see, there are already changes, right? Like you see this area, it's in June, probably crops and vegetation area, they're getting like differentiated in color. So you can already see some changes that look pretty neat because the amount of cloud cover seems quite good. So yeah, we can take a look now at how to do this with R. So I'm gonna confuse you again. Good. That's it. Any questions so far? Yeah.
Just a couple. You have been using a bounding box.
Yeah.
While doing the cube. Could you use a little small one so that you only focus on your area of interest?
Of course.
At that moment you use it.
You can definitely do that. So that's what I don't know when. I will show you later. But for example, here, like this is a smaller one. I thought also like I want to just look at the crops, for example. You can do that, but you can like here I create a new cube, but you can definitely also just say, okay, now just extract this smaller bounding box. Like you can do it with iCell, like I did before, that you say, okay, I just want this selection of from this pixel to this pixel. Remember, I was doing that. But that's hard because your head is not computing the pixels, right? So that also took me a while. So you can do the same way, this selection and getting this smaller area. You can do that as well, already with the cube. Yeah, so it's like the same way as reducing it in time, you can like chunk it down to an area of interest.
But can you do at the moment of the definition of the cube?
Yes, like
at the beginning, I think, of the code, you use stuff, you know?
Yeah, it's exactly that. So like in this in the previous case I gave the Poznan bound, and in this case I'm giving a smaller one. So we can take a look at this already.
Okay. So it will crop it automatically.
Exactly, it will just create a new cube with a smaller area. So and in this case, for example, I called it with 10-meter resolution because I thought, okay, this would just work. So that's exactly what I'm doing here. I got a smaller area with this with this GeoJSON. I just recreate the cube with the items. I say I want this in 10-meter resolution. That's the reason why I didn't just crop the previous cube, because I had it in 200 meters. So now I want to have a new cube in 10 meters. And then you can give this smaller bound area. Then I do directly the selection of red, green, blue. And then I have my RGB representation of a smaller type of chunk. Yeah.
Using resampling, because all the bands needs to be resampled at 10 meters. So 60 meters band can still be at 60 meters.
Exactly. So like basically every band that is also in 20 meters or 60 meters will get resampled to 10 meters. And that's where the resampling becomes even more important. Because yeah, you have to basically downscale. So that it's gonna like chunk down the pixels, but still you need to think about it. Yeah, for sure. Yeah. So yeah, so that's basically what we're looking at. This is I was just wanting to visualize a smaller area. So since we already started talking about it, I can a little bit go on. Yeah, we have this other new cube that is now 10-meter resolution. So you'll see it here. And then we can like just take a look at what we got with this. So we have again the 8 timestamps. And what I did here is create a crop of this data so that you can see how this changes. Not a crop, a GIF. And you can see how this then changes over time. So these are my 8 scenes just looping over. Yeah.
Just make sure all this is in memory, right?
Now this is in memory because
like,
yeah. I call computer.
How could you do for exporting?
You want to export
the extension of the file in nets?
Yeah, I think that's actually probably in the documentation in a way, but you could definitely like save all this information when you already have it. You can export it as an TDF. I think even GeoTIFF allows you to have now a bit more of this data process, or you can just export every scene in one GeoTIFF. That's also like one way to do it, but yeah, NetCDF could be a good way. I'm usually not exporting the data, so like because I like you can do a lot on the cloud, and normally when I really have to export a result, it will be like the last step of everything. So I wouldn't, in my opinion, export like a bunch of scenes for then doing work locally when you can do so much. So like, for example, if I in the end want to just have a composite of NDVI or something like this, then I will just get the final GeoTIFF and then continue working with that. Or if I'm only interested in time series, then I will just export a CSV, for example, and not export all this data, because that's like, for me, that's the main advantage of working with Stack, that you don't need to get all this in your own laptop. You can just work and process things and then have like the final product with you. But I see the need to also sometimes have these individual things. So.
No, I was wondering this because I was thinking about the X cube.
Mhm.
So probably there is a way of integration already in the cloud. So we don't need.
Yeah, I would hope so. So yeah, but I mean, Xcube is a little bit like, I didn't know about it before this summer school. But I have the feeling it's quite similar to what you can do with Stack. But it's really like their own solution. So I was talking to Alicia before, and I was asking her if they're also planning to have a Stack implementation, so you can have all the data on Stack and then do stuff. And she said that they're working towards that. That's quite a priority, that they want to have all their Stack data catalog also there, so that it's also going to work, right? Like you can also fetch the data in that way. So there will be for sure ways of integrating and doing things. Yeah, definitely. Yeah. So yeah, this is the nice GIF of crops, and you can see them changing. And okay, we can go on in this direction, where you can do calculations, like for example, NDVI. So you can say, okay, from this nice cube that I have now, I want to compute the NDVI. So for that, you can say cube, I want to select the band near infrared, and I want to select the band red. I find this Python syntax very funny, where you can just create two variables in one single line. But okay, so I have this is the near infrared is this, and then the red is this. And then I compute the NDVI, which is just, we already know, near infrared minus red divided by near infrared plus red. And then I have this new cube with NDVIs. So as you will see here, I have now my 8 timestamps. I have my X and my Y, but I lost all the bands. You see that, right? I don't have this extra small thing here that shows me the bands. And that's because I just basically combined all the bands into the NDVI. So that is not there anymore. I only have time X and Y. I don't have the RGB anymore. So remember from the exercise that we did yesterday with Sentinel-1, you can definitely concatenate this back into your cube, and then you can have it as an extra, as an extra band. You can have the NDVI on the same cube if you want to do then other type of processes and things. It can just be one extra band. But in this case, we just created a smaller cube only with NDVIs. So I can ask different questions to this cube. So I can tell it, okay, I want to get like a composite with the maximum NDVI value. And I want you to look over time, like what is the maximum over time for each pixel, right? So like if I have 8 days, 8 dates, I want to get a composite of the maximum NDVI for each pixel on that date. In the sense, when there was more vegetation for each of these pixels. Yeah, I see you looking at it. I don't know if I get you, but I will show you. So in this case, like I'm only reducing the whole thing by time. So I don't have anymore all the time values, but I only have one scene with each pixel is composed by the maximum value of NDVI per time. So I don't have time anymore. I only have one single raster with the max NDVI. And then I can compute this again and plot it. I actually don't know how long this is taking because I was doing this technique of letting things run while I'm talking. So let's see. So the idea here would be to just have this composite. You can also not do the max, you can also do the mean. So what's the mean NDVI for all my time steps, right? And then I can like do some analysis. In this case, I want to go do the max. So then you will see here, you have one single value where you have the least NDVI, so probably built up area, and the maximum NDVI in my time series, where you will have most likely the forest really, really green, and then you'll have some crops you will basically get when they were at their maximum. Yeah, that's basically it. And what we can also do is compute what we like, it's called an anomaly. So let's see how much the NDVI deviates from this from the mean of the collection. So like if you have the max and then you can compute the mean and then you say, okay, what is the difference between the two? And then you can see where there is like bigger changes, right? When there is like a big change in between. That's just one of the applications. So for that, we do this composite of max minus the mean. And I call that anomaly. And then we can see this, right? We can have a look at when was the, like, what are the areas that changed the most? So you see here, there's not like, this is a positive anomaly because there was like increase. This is a negative anomaly, it's a decrease. And then in other ways, it's staying a little bit constant. Yeah. So these are just some of the things that you can do. Like the idea here to show you is that you can already do a lot just with Stack without the need to download. So for example, this would be, if this is the aim of my analysis, I would end up only downloading this TIFF instead of my whole data set because this is my aim product, right? Then if I download this, then I can already use it on whatever thing that I need to communicate to partners or whatever, then I can use this already as the final product. Yeah, so then this can be exported as a TIFF most likely, and then you can download it. Okay, so this is, how am I doing with time? We'll manage. Here is also this, again, like this download part of it. You can download for sure each of the items that you queried from Stack. I don't put this on an executable code because I don't want you to do it, but you can do it, right? You can definitely say, okay, I want to download each item on the collection. So that's where there is a for loop. And then you just basically start retrieving all this data locally. I don't know what you want to do it, but anyway, I put the code snippet there if you want to do it. Okay, good. So now let's go to R and let's see how to do this in R. So here they decided to come up with a name for the package that is not a tongue twister. So here we're gonna do Stack Data Cube with a package called GDAL cubes, or actually, like, every time I have Roger Vivant around, I'm thinking I have to call it Goodle cubes. So Goodle cubes are is the package that we can use to make these data cubes on demand. It's incredibly powerful and you can do a lot. And this is already something that Marius Apple presented 2 years ago in the summer school. So I'm sure you will get a lot of more data, and there's a link to his presentation at the end. But yes, I thought it would be a nice comparison between the two. So we will use this one. And in this case, I'm going to start it a little bit more clean in the sense that I will already do some pre-selections so that things are not like too big as on Python, but you can also do this with the Python stack. All right. So again, here, first in this line, I'm just selecting which bands I'm gonna call. In this case, as you see, the bands are still with numbers. And that's because we're using these Sentinel-2 cogs, like the version 0. So that's why they're not named. You remember how the items look like, right? Like it's from this query at the top. Here we query the items and then to get each of these features. So as you see, this is in features. So that's why we do this $sign features. And then we say, okay, with all these features here, not all of these because this is a little bit more queried, but with these features, you can please create a data cube for me. And yeah. And here we give which assets we want, so which bands we want to use on our data cube. And in this case, we're going to do the filtering already on the items that we got from Stack. So in Python, we did this filtering when we searched the collection. In this one, we're going to do it when creating the cube. So again, you create like a function where you say, okay, I want the EO cloud cover to be below 10%. And I want everything that has a valid cloud cover for this particular collection. So, and we can create the cube like this, and then we'll just get our information of how our cube looks like. The print method is not amazing for Quarto, but let's go through everything that's printed here. So we have 28 images with 12 bands. These are the bands. So all these, these are the images. And these are the bands. Band 1, 2, 3, 4, like 11. And yeah, that's the data that you have. That's how your cube looks like. It's not as a nice cube representation print method as in Python, but it's more or less what, yeah, you can picture it now in your head. You can do the cube, right? And now we can do directly some visualization of the data. So for that, we can do some, we fetch the function cube view. And with cube view, we're gonna get an AOI that we already defined. But in this case, we need it in 3857 because it's gonna do the plotting on Web Mercator. And that's why I did this bounding box 3857 before this conversion of my bounding box, okay? So for this, viewing this cube, we're gonna create this cube view object, I call it V. So you have the reference system, in this case 3857. So we give the extent, this is the time extent. So this is all these features, all these values that we fetched before. So like here we have the time extent. That's why I gave it as a vector and not completely glued together, because then I can fetch each of the dates. And this is the bounding box that I was using before. So here I have that. Then I can give it again a resolution. So it just looks a little bit different, but this is the same, right? Like this is how much I want the resolution in X and in Y, meaning that you can also give different resolutions. So you can say in X, I want it to be 100, and in Y, I want it to be 200. That also works. If you want to do that. I don't know if you want to do that, but you can do it too. So you're not bound to just a square, but you can work with rectangles. And here you have to give the temporal resolution. So the temporal resolution here is P1D. So it's a little bit cryptic, but this means 1 day. You can give it another type of resolution. So like I ask here a quiz, like how would you use biweekly, but let's see how you would use other things. So like we can always go to the documentation. That is one thing that I love about R. You can always go to the documentation and take a look at what's going on and what should we do. So like this DT object in here, for example, tells you what is the size of pixels that you want in the time reduction. You express it in this ISO 8601 period string, and you can say every 16 days, for example, or every something, something, something. So like if you look for this, you will get all these conventions and how to do this properly. Wait, probably this is not it. And how to choose like different types of conventions. But okay, you will find it for sure. But this is the way you define the time in this format. Then we say how we want to aggregate this whole thing. So again, we want to do the median. And in this case, I'm using a resampling method average. So how is it going to do this thing? I'm not using bilinear anymore. I'm using average just to show you that there are many ways. And if you read the documentation, you will find the one that is suited for you. Good. Yeah, but so this is how you create this cube view, and we will go to this in a minute, like to actually see this, but we're basically setting the framework of what we want, right? We want this timestamp extent, we want this resolution, we want this time, we want this type of aggregation, we want this type of resampling. Now, what we can also do is do some cloud masking. So this is based on SCL values. So SCL values are based on a level 2A algorithm, which is basically a scene classification. So you get this whole workflow that they did from TOA, then they classify their data, and then they get basically some cloud snow detection algorithm, brightness, like a bunch of things that you can get from this. There's like a lot of processing done, and then you basically get this in this classification value in the end, where you have this one extra layer in your data that has no data, what pixels are saturated or defective, what are shadows or cloud shadows. vegetation, water, whatever. But the important thing here is that you have it per pixel. That means that you can really create composites with like taking out the cloud pixels, but per pixel, and not looking at the whole scene. So that is helping you a lot. So that's what we're gonna look at now at how this looks like. So like how one of these scenes looks like. And so for this, I just took one of the items that I have, and yeah, I just pulled the first item. I think I did this before. And then I just read it with Rasterio so that I can take a look at what this is. So I'm asking for this scene classification layer just to show you how it looks like, right? I have here a CSV with the classes just to make my plot pretty. But yeah, it's just to show how this looks like. And this is how one of the scenes classification would look like. So you have basically all the information of what is a cloud shadow. So you see this brownish, you have vegetation, you have non-vegetated, you have water, you have anything that is unclassified, you have cloud probabilities and cirrus. So basically with this, you can per pixel say, okay, I want this in my cube, I don't want this in my cube. So you can do an extra sort of, yeah, filtering your data, right? So what you do here is define a mask. That's the way that you would do it. So in this case, we say, okay, I want this mask and I want you to mask these values. So when I saw this in the documentation, it was like 389 and I was like, what is this? So that's why I made this plot. 3 is cloud shadows, 8 is cloud medium probability, and 9 is cloud high probability. So I'm basically gonna say, everything that has these values on the scene classification, please avoid putting them on my median view because it's just gonna mess up my data when you calculate the median. I don't want them there, right? So that's what the masking is doing. And yeah, you can specify that when you're working. Whoop, I forgot to run B. Yeah, so I forgot to run B. So that's basically what I'm telling them this to show me. This RGB, sorry, this is basically when I want to do now the viewing representation. I can pass this mask and tell it, okay, I have this V object where I defined all my extent and everything. I have my collection, and I want you to mask everything with this mask values that I just gave you before. So here we're gonna do an RGB reduction with the mean. We select the bands, so you need to know the bands. Blue, green, red in this case, that's how they're, right? Yeah. And we reduce it by time. So we have, we're gonna say, okay, so we select the bands and then we say, reduce by time each of these bands and get me the median of each of them. So then I have my cube with a mean value for all my stuff. Then I can plot this, and I don't know how long this will take. So again, this is the moment when all the data is going to be fetched, right? This is the moment when I'm going to tell the Stack API, okay, now I defined everything I wanted. Now I want you to do a visualization for me. So in this case, we don't have compute or task or anything, or maybe there is some sort of parallelization happening in the background. I'm not completely familiar with that, but this is only the moment when you will get everything. I will not run, well, maybe I could try to run this. This is probably going to take a while, but wait, I should have done that. Shoot. Oh yeah, okay. I'm not going to run it because we're not completely thing, but I copied it before what the result looks like so that you can see it. And yeah, this is it. This is basically the representation that you would get. Once you fetch all the data, you get a median composition of your data that you already fetched from the Stack API. So that's what you can do with GDAL cubes, and it's pretty powerful as well. So I have added some exercises for you. You don't need to do them now, you're probably tired. But if you want to play a little bit on how to do this computation of the MDVIs and the anomaly that I showed in Python, how could you do this with GDAL cubes? There, Marius has this RSpatial blog where he's looking a little bit into this, so you can follow along there and take a look at how you would do that. And you can also compute time series. So you can also take values outside of this information. Like maybe you can, if you reduce everything in space, so you can reduce in X and Y instead of reducing by time, then you will get information that just for your values. And there you can do, for example, some time series analysis of one single crop parcel, for example, things like this. So this is also something that you can do as an exercise, you have so much free time. And yeah, and for that, you can easily create a GeoJSON with this geojson.ai. And yeah, just play a little bit along. You can have some sort of temporal grouping so that your analysis is not so crazy. But if you're really gonna use this for your work, then for example, you can do yearly analysis or something like this, and then have this mean NDVI value per month or something, whatever really suits you, right? Like this is quite a powerful tool where you can just really play with everything that you have and use it really more in production. Yeah. So as I mentioned before, this is really inspired completely on Marius' talk from the OpenGeoHub 2021. So do check his repo and his video. He's giving a lot of info over there as well. But in this one, as I said, I wanted to do this comparison between what you can do with each. So I think I'll stop talking and ask if you have any questions so far or any doubts, or if you found it interesting. Will you be working more with the R implementation, the Python implementation? What do you think? Julia, all right. I forgot completely to add like a Julia segment on it. I should have asked Martin to let's do it. I'm pretty sure if I ask him, he will come up with also a notebook on how to do this in Julia. I don't know if it's advanced enough, but with all the packages, but why not? You could be the first one to do it as well. No, thank you. All right.
To me, it happened to use this data, but I actually use derived product, so not the raw images. Is there any way to include derived product? I mean, are there derived product in Stack catalog?
And it depends which catalog you look at. So now we're looking at this Earth data one, but there are many other like catalogs that you can query. Probably these derived products are more in catalogs that you have to give credentials, but you can definitely query that. So like you just need to give your credentials to the Stack API, like the Stack package, and then it will just fetch you anything. So you can also work with Microsoft Planetary Computer, with Google Cubes, or you can work with Earth Engine. I mean, yes, you can work with anything that you have credentials to and that is on Stack. So the Stack catalog is quite big. It's not only for Sentinel-1 or Sentinel-2, you have Landsat, as I said, but you also have Copernicus data services. So like you have all these other things. You also have climate data, I believe. It's quite big, and it's getting more and more convention on how to share this raster data, like how to establish well the metadata and stuff. So for sure, you'll find a lot, and they will always have good instructions on how to fetch that data as well. So yeah, that should be there.
You just need to find an URL.
Yeah, you need to find the URL. So this Stack catalog link that I gave will give you all the collections that you have, so you can browse through there what is available. They are very comprehensive.
And can we find the old data of NDVI from the 90s or something like that?
NDVI from the 90s? Probably, yes. I mean, that's probably computed from Landsat, but there's also some derived products, I think. I'm not sure if I'm going to say this correctly, but Modis maybe has some data as well. But that's...
This was later.
Sorry?
Modis doesn't exist in the 90s. Though.
I don't know. I thought so.
Okay.
Okay.
Yeah, that's ADH or
All right, then thank you for the correction. Probably from Landsat, then for sure you can get quite some good data. I mean, it's 30-meter resolution, it's good enough, and you can definitely compute NDVI from that, and you can do this sort of analysis with Stack API. That's also, I think, on the Earth data also available. And they've been working a lot in making it harmonize all this Landsat 5 to Landsat 8, or is there Landsat 9 already? Yeah. Landsat 9. So everything is like more harmonized, and there's even a product, I think I mentioned it yesterday, the harmonized Landsat Sentinel, where all of them are like combined together. So for any data holes or like for increasing the time series that you have, you can also use that. And probably with that product, you could compute like a really long-term NDVI thing. That would be interesting to see. I think it's already on Stack in one of the collections. I don't remember which one, but I can take a look. Yeah,
Okay, thank you.
sure. Any other question? Yeah.
I don't know if that was to you. Sometimes when I query for many images, not all of them, many scenes, not all of them are at the same bounding area.
Uh-huh.
Sometimes one scene is just a little piece.
Yeah.
And do you manage to, I don't know, use something to integrate that image into others? Otherwise, you only have data for a little.
Yeah, this definitely happens. And this is with Sentinel-2. The reason for this is just because there is no data in this part. So Sentinel-2 collects the data in a very systematic way that every scene will really be the same scene every time there is a repeat pass. So these bounding boxes things should not really be the case. That is not that the sensor passed slightly on the side. It's just that there must have been something there that you have no data. So remember that I show you how to take all the scenes that have no data. Like you want the coverage of 80% of the scene. So that's one way you can deal with it. And of course, there's no data. You can also ignore it when you do your medians. You just don't want that, of course, in there. But you do want this one part maybe. So that's one way to do it, definitely. Yeah. More questions? If not, thank you so much. And I think we can call it a day. And we're done with the summer school, I guess. Good. Thank you.